Let's look at heat transfer between a series of objects that are all touching each other, or you can think of it as one long, skinny object where I'm imagining it divided into imaginary slices like centimeter by centimeter or something. So this is heat flow in kind of one dimension as opposed to the other video we just did, which is kind of more like 0 dimensions. So I'm going to say I have 9 regions, so I'm tracking temperature 1 through temperature 9. And I'm going to say it starts at 20 degrees, which is a somewhat cool room temperature sort of thing, 20 degrees Celsius. And let's say this is like a rod that I'm roasting a marshmallow on, or going to roast a marshmallow on, and I'm sticking one end of it into a campfire that's at 300 degrees Celsius. And at the other end, I'm holding it with my hand, and my hand is at maybe 30 degrees Celsius. So we want to think, how does the temperature in the rod end up changing from the campfire end to the hand end? So I've got basically the same setup I had in the other video, where time is moving along. I've got dt, and so now I'm going to need a derivative for each of the regions of my object that I'm keeping track of. Also, I'm presuming that all the heat stays in this system, that none of it leaves out the sides of the long object. So you could assume there's insulation, maybe pipe insulation or something, or you could say, well, air doesn't transfer heat all that well, but campfires sure do transfer heat well, and maybe your hand on a metal object transfers heat well. So you could say, well, even if the sides aren't insulated, they're just not losing heat very much. So let's think of what we want for, let's say, the derivative of the temperature in region 1. Actually, let's do region 2 first. It's often easier to start in the middle and then worry about the end conditions later. So we can do the same basic thing we did before and say heat transfer coefficient times the difference of the temperatures. So I'm tracking temperature 2 here. So I can look to the right of it, just like we did the other time, and subtract the current object temperature. That way, if temperature 3 is higher than temperature 2, we'll get a positive difference, and that means heat will be flowing into region 2. And then we could say, again, so that's heat from 3 to 2. Then we could say there's also heat flowing from 1 to 2. So we'll take temperature 1 region minus temperature 2 region. And that's it. And right now, that's 0 because temperatures 1, 2, and 3 are all the same. But I could copy that and paste it here. And then we see, oh, there's a fair bit of heat flowing from the 300-degree campfire into the 20-degree object here. So we get 84, and we can't really see it in just this number, but there's no heat flowing the other way. So here's the question, what happens if I copy this formula and paste it over here? Well, now it's reading what it thinks is the temperature of this region, but that's not even a temperature. So I might need a different formula here. And I'm going to say that the campfire just maintains its own temperature. It has so much heat to it that it doesn't really care that it's losing heat to the metal rod here. So I'm going to just put a 0 here. And then on the next row, I'm going to say equals the number above it. And that way, when I fill down, the derivative of temperature 0 will just always be 0. I can come over here. I've got all my other derivatives laid out, so I can fill this over this way. But a negative 12, does that make sense? Well, that's using temperature 9, 10, and 11, but there isn't really an 11. So I'll just say again, my hand, it's connected to my body. I'm, let's say, a mammal, and my body's good at regulating temperature, so the derivative of my hand temperature is just going to stay 0. All right, so now we'll go back and say, what's the new temperature based on the old temperature and the rate of change? So we'll say equals previous temperature plus the rate of change of temperature 1 times delta T, and we will put in a $sign before the column on that, so when I fill it left to right, it will keep referring to the delta T column. And you might be wondering about the coloring. I'll explain that later. So let's go check over on this side. Okay, that's saying the previous value plus temperature 10 prime times delta T. And going to do the same thing over here. It looks like it's doing the right thing. You know what, I'm going to, so this is conditional formatting. I'm going to wipe that out for now and put it back in later. So we're going to clear the rules on that. Okay, so now I can fill down all of those, and I can fill down, actually I want to fill these down, fill this one down. So take a sec to imagine, before we graph it, what these temperatures will look like when we graph it. You can see there's some heat kind of leaking in, not exactly leaking, but flowing in from the side here. There's some heat from my hand, which is warmer than the object, flowing in from the side here. So let's graph time versus all these temperatures. And so let's see, this last dt doesn't make sense. We'll delete that. So think about what the axes are here. We'll put in axis title. So the axis title for the x-axis is time, and the axis title for the y-axis is temperature, degrees Celsius. So you can see we've got the campfire staying at a constant temperature, the item right, or the region right next to the campfire increasing, the region right next to that increasing, but not as quickly. And you can see there's a little bit of a concave up segment here, and then concave down to the temperature of region 2. And then you can see, yep, maybe that's doing what we expect, maybe not. Here's a fun trick. This doesn't show you a cross-section of the temperature of the rod at any time. So I'm going to copy the graph, paste it, go to Design, and say Switch Row Column. Now this is a little hard to think about what it is, but now instead of time being the x-axis is actually location. Let's try that again. Region or location. And the y-axis is still temperature. So this is saying location, let's see, maybe this, let's highlight the data. Okay, so we need to only show the actual temperatures there, not time and dt as apparent temperatures. So this is saying, as a cross-section of the rod, it starts out 300 and then basically 20 all the way over to where my hand is. But then as time goes on, it's becoming, what would you say that is, kind of an exponential fall off, but then kind of a rise over here. So that's kind of interesting. We can also go change the heat transfer coefficient. Remember that heat transfer coefficient is something per unit time. We could say we're changing the time units, or we could say let's do time units that are twice as big. And then we see this is approaching the 300 degrees faster than it was before. Right, so that's heat flow in 1 dimension. And in the next video, we'll do heat flow in 2 dimensions. Oh, I forgot to use conditional formatting here. So one way to do that is to, but maybe we don't want to use the 300 and the 30 to set the conditional formatting scale. So we'll just highlight the temperature of the actual item that we're tracking. And we'll go to the Home tab, conditional formatting, color scales. We can say color the largest numbers red and the lowest numbers white. You might think, well, let me color the lowest numbers blue to indicate very cool temperatures. You can do that, or you could say, well, maybe blue should be saved for negative values. You can't have negative Celsius, that's true, but you can't have negative Kelvin, so you could go either way on this. Let's try this. Sometimes it helps to zoom out. So there you can see, let's try that again. one end of the rod is getting hotter and hotter, and the original cool temperatures are just kind of fading out as the heat filters in from one end of the rod. All right.